So far, in all the mathematical formulations we have done for any physical system, we always come from the side that we have defined the characteristic of the system and then try to fit in an approximate function to get an exact displacement function out of it. So basically we pick up a certain approximate function and we hope that it's the right one. Whereas the characteristic or the differential equation is already set up for the behavior of the system. Now, with what we want to do with finite elements is that we want to enforce certain approximate behavior of the element already. Okay, so what we want to do is we want to say that there is a certain element and it shows a certain behavior. Now we can see whether that element satisfies the certain given condition or not. This is the other way around. So what we want to do to define the approximate behavior of the system now is to enforce a certain deflection method or mechanism already. And these approximating functions that we use to enforce a certain behavior or deflection of an element are called shape functions. So we can enforce exactly how the element will deform and then derive results according to this particular enforced behavior. So you must always remember that whatever function that you have defined as a shape function is the inherent behavior of the element. It's not going to do anything other than what you have enforced it to do. So if you have defined or enforced an element to be a linear element, it's not going to show you quadratic behavior. That is something that you have to keep in mind. It's not magically going to show you a better result of what you're expecting. It'll show you exactly what you should expect. So let's just take an example again, because I want to give you a short introduction to shape functions now through this video, so that you can go back to the Galerkin approach. But this is also just a general introduction to shape functions as well. Okay, so basically what you're doing is that you're defining the behavior of an element in terms of deflection, and you are basically enforcing it. So don't be surprised when it doesn't do what you want it to do, but it will do exactly what you asked it to do. Let's just look at a simple shape function of the kind of member we've been looking at till now. So what we've been seeing is that we have just a 1D element always. It has two nodes, I and j, let's say. And we can say that you have a displacement here ui, and here you have a displacement uj, and it has a certain stiffness k. Okay, and it can only move along the x direction. So it's just a 1D element. We don't need the k here, so I'm just going to get rid of it for now. I'm just looking at the deformation behavior or enforcing a deformation behavior. Now I wanted just to show a very simple behavior in terms of x, which is linear, right? So I just want it to be a linear deformation. So for a linear deformation, we are going to enforce a certain condition such that the elemental deflection ue, sorry, let me change the color here, is given as a linear polynomial, which is quite simply written as c1 plus c2 into x, because it's changing along x according to this elemental behavior. Now, we know that there are two nodes. We've defined the two displacements, so we want to enforce the same displacement behavior at every node. So we can quite easily write ui is equal to c1 plus c2 xi, and uj is equal to c1 plus c2 xj. Right, so if I call this equation 1 and I call these two equation 2, then I can solve equation 2 simultaneously for, so I can say solve for c1 and c2. So if I solve for c1 and c2, then in terms of ui, uj, xi, xj, I will get c1 to be equal to ui xj minus uj xi by xj minus xi. I'm not going to solve it completely because it takes a long time, but of course I'm also copying it off a piece of paper. So if you do the full solution, you'll probably get the same answer. If you don't, please do let me know. So you have uj minus ui as C2 by xj minus xi. Now we know that xj minus xi is equal to L because that's the length of the element we are assuming, so we can replace here and here as L. Now if we substitute these equations 3 and 4 back into 1, then you can write the elemental displacement function ue to be equal to, and you have to put it together in the right format so that everything comes as coefficients of the displacements at the nodes. Then you would get x minus xi by L times uj. So now you have everything in terms, very neatly in terms of the nodal. Of course, please work through it. So don't just copy what I've written, but also work through it when you are doing it on your own. So pause the video and go through and see if everything checks out for you. And of course, L is given as the length of the element. So I have a displacement function here in terms of the nodal displacements for the element. Now, if I want to write it simply, then I can also replace the coefficients by ni and nj for the different nodes, for the nodes I and j. Right? So these ni and j are nothing but the behavior of the displacement at each node defined as a coefficient, and this ni and nj are nothing but the shape functions. So the shape functions, one of the characteristics which I want to point out now is that the number of shape functions for every element is equal to the number of nodes in the element, or the number of degrees of freedom, sorry, not nodes. So if you have 2 degrees of freedom per node, then you will have 2 shape functions defining the 2 degrees of freedom. In this case, we just have one at each node, so we have only one shape function at each node for the displacement. Now further, I can write this also in a nice matrix formation. So I can say therefore u of the element is given as ni, nj, ui, uj. Okay, so a very classic form of writing the shape function. Now I also want to pick a small example, and I want to say, okay, this element that we worked with, let's assume that it has the nodes I and j, and it has a certain length L, and this is actually where x is equal to L, and this is actually where x is equal to 0. So basically what we are enforcing is that xi is equal to 0 and xj is equal to L. So if I just get the shape functions back from the previous slide, then I will get ni is equal to xj minus x by L, and nj is equal to x minus xi by L. Right? So if I now substitute the value of xi and xj, then I would get ni is equal to 1 minus x by L, and nj would be equal to x by L. So this is the basic formulation. This is a basic shape function of an element which is of length L, and that's the only element we are talking about. Then in that case, this shape function checks out perfectly. Now, if you look carefully at the shape functions themselves, there are certain characteristics which I can point you out towards, right? So if you look at the value of ni and j at different positions in the element at the nodes I and j. So let me make a little table here. So I have nodes I and node I and node j. At node I and j, I have the value of x. So let's just say node, and then I have I and j. X at I is 0, x at j is L. Ni at x is equal to 0 is equal to 1. But Ni at x is equal to L will be equal to 0. The same way, Nj at x is equal to 0 will be 0, but Nj at x is equal to L will be 1. So what we find out is one of the very interesting characteristics of shape functions is that the shape function is always unity at its own node and 0 at the other. So this is Ni. And in the same way, you will see that the Nj is also unity at j and 0 at I, like I just showed you. Now, one more fun fact about the shape functions is that the sum of the shape functions at a particular node is always equal to 1. So if I look at the summation, I get 1 and 1. Of course, this is quite simple, but you could look at more complicated function and say it always turns out to be unity. When we do much more complicated elements, you will see much more characteristics. So I'll be happy if you could point out to some of the characteristics later on yourself to me before I do it. So I'm looking forward to that. Let's just go through a little recap because this was a very short video. So the shape functions are basically definition of forced behavior, let's say a forced deflection function on a certain element for its characteristic. So in this case, we picked a linear function, and this linear function therefore has to be applied to every node. So every node will show the same deflection character. And then you can work through it, find the unknowns, and get a certain shape function. So once you know the shape function of a certain element, it always stays. You can just use it again and again, and then you don't have to do this entire derivation. For example, if you just have a 1D element which is moving along x, and you wanted to have only a linear displacement, then you can just directly use these shape functions that we have already develop for you here, or derive for you here, which you can also do for higher order elements, for different kinds of elements that we will talk about later.